Hey guys, welcome to our third lecture on the extended Euclidean algorithm, or Euler's Totient function in orders. If you're not already familiar with modular arithmetic, you can read our modular arithmetic handout. You can find it at this simple bit.ly link. Make sure that you understand congruences before continuing with this presentation. As a refresher, let's go over the Euclidean algorithm. Basically, the algorithm stems from this one fact that the GCD of two numbers a and b is equal to the GCD of a minus b and b. Basically, what you can do is to simplify the numbers in the GCD. You can subtract one number from the other and keep doing that. And then once a becomes less than b, you can subtract a from b. And then you just keep subtracting until both numbers get small enough to where or until one number actually reaches 0, at which point you know the other number must be the GCD. So here's an example. Suppose you want to find the GCD of 72 and 30. What you do is you subtract 30 from 72 twice. So to get from the first step to the second step, you do that. That leaves you with 12 and 30. Then you subtract 2 12s from 30, which leaves you with 12 and 6. You subtract 2 6s from 12. You're left with 0 and 6. And that's just 6. So 6 is the GCD of the two numbers. Alright, so that's basically the Euclidean algorithm. And what we can do is basically extend the Euclidean algorithm so that we can actually compute the inverse of a number modulo another number. So suppose we want to find the inverse of 17 modulo 114. I apologize, the superscripts did not come out right in this presentation. So we want to find the inverse of 17 modulo 114. In other words, we want to find x so that we want to find an integer x so that 17x is going to 1 modulo 114. Alright, so what we do is we set up a so-called augmented matrix. And, well, first actually, what we can do, we set up an augmented matrix, alright. We start off with this identity matrix on the left-hand side, that's what they call it, the 1 0 0 1. And we put the numbers 17 and 114 on the right-hand column and separate them with a line. What this matrix is supposed to tell us, or is supposed to translate into, this is that 17 times 1, that's the 1 here, plus 114 times 0, that's the 0 right here, is equal to 17 on the right-hand column. And what the second row of the augmented matrix is supposed to tell us is that 17 times 0 plus 114 times 1, though they correspond to the 0 and 1 here, is equal to 114. And obviously these two equations are true, right? So what we can do is we can actually subtract this first equation from the second equation to get that. So we keep the first equation. And when we subtract the first equation from the second equation, we get 17 times minus 1 plus 114 times 1 equals 97. And what this so in this matrix translates into 1 0, or these two equations translate into the augmented matrix 1 0 minus 1 1, 1797. So essentially, to get to this matrix from this matrix, we took the first row of our original matrix and subtracted from the second row. And what we're basically going to do is we're going to keep subtracting one row from another row as many times as necessary, like in the Euclidean algorithm, until one of these two numbers simplifies to 1. All right. So let's do that. So we're at this matrix, and what we want to do is we want to keep subtracting one row from the other until one of the two numbers on the right-hand column becomes 1. All right, so let's do that. We can subtract 5 times the first row from the second row. 5 times the first row minus the second row gives, let's see, 6, 1, 17. 17 times 5, that's 85, so replace with 12 here. Alright, so we're now there. Keep moving along. We subtract the second row from the first row. 7 minus 1 minus 6, 1. Second row doesn't change. 5, 12. We subtract 2 times the first row from the second row, which gives what? 7. First row remains unchanged. Minus 20 and 3. 2, alright. Subtract 2 times the second row from the first row. The second row remains unchanged. I end up with the 1 here. 47 minus 7. Alright, so now we finally have a row for which we have 1 on the right-hand column. What does that first row mean? Well, it means that 47 times 17 minus 7 times 114 is equal to 1. Why is that useful to us? Well, if we take both sides modulo 114, it means that 47 times 17 is congruent to 1 modulo 114. But this means that 47 is the inverse of 17 modulo 114. So, to summarize, essentially what you do is to find the inverse. Is you set up this augmented matrix. Let's get rid of all this extra stuff going on in here. You set up this augmented matrix, and you keep subtracting one row from the other row until you end up with a 1 in the right-hand column. And then that corresponding equation gives you the inverse. Alright, so the reason it's called the extended Euclidean algorithm is essentially what you're doing is performing the Euclidean algorithm in the right-hand column and keeping track of the matrix in the left-hand column. And that extra matrix is the extension. Alright. Here are a few extra videos on the extended Euclidean algorithm if you're interested. Alright, let's move on to Euler's Totient function. So Euler's Totient function, evaluated at any positive integer n, spits out the number of positive integers less than n that are relatively prime to n. For example, suppose we want to find phi of 10. Well, let's list out the numbers less than 10. and figure out which of them are relatively prime to 10. Well, 1 is relatively prime to 10, 2 is not, 3 is, 4 is not, 5 is not, 6 is not, 7 is, 8 is not, 9 is. So we count 1, 2, 3, 1, 2, 3, 4 integers less than 10 that are relatively prime to it. So phi of 10 is 4. All right. It turns out there's this nice, there's this nice formula for the Totient function, whereby you multiply n by 1 minus 1 over p across all prime divisors of n. Let's do an example to see how that actually works in action. So we want to find phi of 36. So what we do is we take 36 and multiply, well, actually first, sorry. 36 is 2 squared times 3 squared, so the only prime divisors of 36 are 2 and 3. So what we do is we take 36 times 1 minus 1 over 2, because 2 is the first prime divisor. And we multiply that by 1 minus 1 over 3, because 3 is the second prime divisor. That leaves us with, strange, all right, 36 times 1/2 times 2/3. The 2's cancel out. You're left with 12. All right, now suppose we want to find, as another example, just to get the point across, phi of 30. 30 is equal to 2 times 3 times 5. So this is going to be equal to 30 times 1 minus 1, 30 times 1 minus 1 over 2, because 2 is the first prime divisor, times 1 minus 1 over 3, because 3 is the second prime divisor, times 1 minus 1 over 5, because 5 is the third prime divisor. This gives 30 times 1/2 times 2/3 times 4/5. Again, the 2's cancel. What are we left with? 3 times 5 is 15. 15 goes into 32 times. So 2 times 4 is 8. So phi of 30 is 8. All right, now to the big theorem surrounding Euler's Totient function. If a and n are relatively prime integers, then a to the phi n is congruent to 1 modulo n. All right. At first, it's certainly not obvious why this actually has to be true, but it's not too hard to see that this is actually going to be very useful, because what you can do is you can use this congruence to simplify powers of a. So I don't know. Whoops. I have no idea what that was. All right. All right. Sorry about that. I have no idea what that was. Did anything go away here? No, it's still here. All right. Strange. All right. So back to the problem. Right, so this congruence is useful because if you have a power of a, what you can do is you can subtract phi n from the exponent of a repeatedly, and then which allows you to work with this more simplified power. You'll see that in the upcoming example. But first, let's actually prove this theorem. The proof's actually not too bad. We know there are phi n integers less than n that are relatively prime to it. So what we can do is we can index those relatively prime integers. Let's call them R1, R2, R3, all the way up to all the way up to R of phi of n. We know there are phi of n of them. That does not look good. All right, so all these are relatively prime to n. So what we'll do, we'll multiply all of them by a. So we get AR1, AR2, all the way up, well, to be consistent, let's say AR3, all the way up to AR phi sub n. All right, so consider each of these products. We know that the R term is relatively prime to n. We know A is relatively prime to n by hypothesis. So each of these terms has to be relatively prime to n. Furthermore, I claim that all these phi n terms in our second sequence are actually distinct from each other, modulo n. Why? Because if, say, ARI were congruent to ARJ modulo n, then what we could, since A is relatively prime to n, we could multiply by the inverse of A on both sides, which would give R sub I is congruent to R sub J mod n. But this is impossible because this sequence, our first sequence, consisted of distinct numbers. So this is impossible. All right, so if our second sequence consists of numbers relatively prime to n and are all distinct from each other, and there are phi sub n of them, that means that they must be a permutation of the first sequence in some order. Well, okay, quick clarification. When I consider AR1 and AR2 and AR3, I'm considering them to be reduced modulo n already. So the second sequence is, so the second sequence is a permutation of the first sequence when considered modulo n. That means that if we multiply all the terms in the second sequence, they should be congruent to the product of all the terms in the first sequence. What does that end up being? Well, what is the product of all the terms in the second sequence? Well, there will be phi n a's. They're going to be R1, R2, R3, yada yada yada, until R phi n. And the product of the terms in the first sequence are just R1, R2, R3, all the way up to R sub phi of n modulo n. But I think you can see from here, R1, R2, R3, all of them are relatively prime to n. So we can multiply by their inverse to get rid of them on both the left-hand side and the right-hand side. But after you do that, you're left with a to the phi of n is congruent to 1 modulo n, which is exactly what we desired. Very nice argument. All right. So, let's do so. This should be 9 to the 3, 1341. So what we're looking for is this. All right. Well, 9 and 245 are relatively prime, right? Because 245 is what? 5 times 7 squared. Yeah, 5 times 7 squared. So first what we do, we can, well, so since they're relatively prime, we can immediately apply Euler's theorem. Phi of, I haven't been consistent. Actually, I'll just leave it here. You typically see it denoted by either phi or the other phi. So one of the two are generally denoted. I'll keep it as this. Alright, so 245 is 5 times 7 squared, so 5 and 7 are the only prime factors of 245. So phi of 245 is 1 minus, phi of 245 is 245 times 1 minus 1 over 5 times 1 minus 1 over 7, which is equal to 245 times 4/5 times 6/7. Oh, that looks like a mess. Times 4/5 times 6/7. Well, okay, so this was 5 to 245, 5 times 7 squared. Alright. It's going to leave us with 42 times 4, which is 84 times 2, which is 168. So that's part of it. Actually, I should have put, so it's just 168. Alright, so 168. So we're looking for 9 to the 1341 modulo 245. This is what we want. We know by Euler's theorem, we know that 9 to the 168 is going to go to 1 modulo 245. Alright. So from this congruence, well, this tells us what we can do is we can keep subtracting 168 from 1341 and still be equivalent modulo 245. So basically what we can say is that 9 to the 1341 is congruent to 9 to the 1341 modulo 168 in the exponent, then this is taken modulo 245. So, alright, let's see. Just a sec. So 1341 is 1341 modulo 168 reduces to 165. This is modulo 245 again. We can actually subtract 168 once again from the exponent to get minus 3 modulo 245. And what the minus 3 really means, the negative power really, is that we can just write this as 9 to the 3 and take the inverse of that modulo 245. 9 to the 3 is 729. 245. 729 ends up being minus 6 modulo 245. We can do this. Alright. We can split up the minus 1 into 6. Oops. The inverse of minus 1 modulo any number actually is equal to minus 1 because minus 1 times minus 1 is 1. So this is just simply minus the inverse of 6 modulo 245. Alright, so at this point the problem reduces down to finding the inverse of 6 modulo 245, and you should be able to do that using using the extended Euclidean algorithm now. It's not too much fun, but you can set up the augmented matrix, do the Euclidean algorithm simplification to finish from here. So enjoy. Alright, second example. We want 50 to the 340. Again, the superscript's messed up in the presentation. Modulo 180. All right, so if you've read the modular arithmetic handout, mentioned it at the very beginning, you know that we can apply the Chinese remainder theorem here. We cannot directly apply Euler's theorem at the moment because 50 and 180 are not relatively prime, but we can do it after simplifying, after splitting it up into 3 different equations using Chinese remainder. And that will go as follows. So 80, let's see, 80. We'll split it into 20 and 9. 50 to the 340 is congruent to 0 modulo 20. It's not too hard to see. So we just need to figure out 50 to the 340 modulo 9. Alright. Well, we need to find 50 to 340 modulo 9 so we can finish with Chinese remainder. Now, 50 becomes what? Minus 4. So 50 is congruent to minus 4 modulo 9. Raise each side to the 340th power. And since 340 is even, the negative sign on the 4 goes away. So we will be left with 40 to the 340 modulo 9. Alright. Now we can apply Euler's theorem because 4 and 9 are relatively prime. Phi of 9 is the 9 times 1 minus 1/3 because 3 is the only prime divisor of 9. So 9 times 2/3, which is 6. So 40 to the 340 is congruent to 4 to the 340 modulo 6. All this modulo 9. Alright. Keep moving. 340 modulo 6. Let's see. 339 is divisible by 3, not by 6. 336 is divisible by 6. So we have 4 to the 4. Modulo 9. Alright, so this is the same as 16 squared modulo 9. Same as minus 2 squared modulo 9, which is equal to 4 modulo 9. So at this point we can simplify, we can reduce to Chinese remainder. We have 4 mod 9, 0 mod 20. Going through multiples of 20 and checking if they're 4 mod 9 gives that 40 is both divisible by 20 and 4 mod 9. So we have 40 mod 180. So 40 is our answer. Let's move on to the orders. This is our third topic. The order of A mod m with A and m relatively prime is the smallest positive integer x, such that A to the x is congruent to 1 modulo m. We write this as x equals ord sub m of A. The order of 2 mod 9 is 6, because if you go 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4 is 7, 2 to the 5 is 5, and 2 to the 6 is the first one, is the first exponent for which we get 1 mod 9, so the order has to be 6. Alright, let's see. With that actually being said, actually I forgot to mention something about Euler's theorem. I'm sorry, I should know who gone so fast. Man, where's it? There it is. Right. So Euler's theorem stated that a to the phi n is congruent to 1 mod n, right? Where a and n are relatively prime. Note that if n is a prime p, oops, can't spell prime, it's a prime p, then phi of p equals p minus 1 because all numbers less than p are relatively prime to p because p is prime. So phi of p is, phi of p is p minus 1. That means a to the p minus 1 is congruent to 1 mod p. For all p coprime, or relatively prime. Well, when is a number relatively prime with a prime number? Well, that holds true if p does not divide a. So we have a to the p minus 1 is congruent to 1 modulo p if p does not divide a. Obviously, if p divides a, then we have 0 mod p. So this special case of Euler's theorem is often known as Fermat's little theorem, by the way. Right, back to the order. So the order is the smallest positive integer x, where such that a to the x is equivalent to 1 modulo m, where a and m are relatively prime. Alright, that's that. Now, why is it important that a and m are relatively prime? Well, if a and m are relatively prime, why is it important that a and m are relatively prime for the order to even exist? Well, if a and m are relatively prime, then a to the phi of m is congruent to 1 modulo m. So that means there exists a positive integer x, so that a to the x is equivalent to 1 modulo m. Namely, phi of m is one such integer. It may not be the smallest one, but at least such an integer actually exists. So the order has to exist, and in particular, since phi m is a possible exponent, it has to be less than or equal to phi m. We'll actually see that our next theorem will show us that it actually has to not only be less than or equal to phi m, it actually has to divide phi of m. Alright, for relatively prime positive integers a and m, a to the n is congruent to 1 modulo m, if and only if the order of a modulo m divides n. In other words, the only exponents for which you get 1 modulo m are multiples of the order. Basically, once you know what the order is, you know what all other possible exponents are. So proof. Suppose first of all, okay, suppose a to the n is congruent to 1 modulo m, and let x be the order of a mod m. Alright, write n as kx plus r, where r is less than k and less than or equal to 0. Alright, we can do this because this is simply by division, right? We're just dividing n by x, and we're getting a quotient, and we're getting a remainder. I should probably call this q, actually, so it's more clear. Q is the quotient, and r is the remainder when n is divided by x. Alright, so we then have a to the qx plus r is congruent to 1 modulo n. sorry, was I using M here? Sorry, this should be all M. I'm sorry. See N before I got confused. Right, so a to the qx plus r, well, that can be written as, let's see, a to the x to the q times a to the r is equivalent to 1 modulo m. Well, x is the order, so a to the x is 1, and 1 to the q also has to be 1. So this leaves us with just AR is equivalent to 1 modulo m. We know R. Alright, so what I'm saying, I don't think it's getting late, so I should probably be more careful with what I'm saying. 0 is less than or equal to R, which is less than x. Sorry. We know that, alright, well, again, I'll just say it here again. We know 0 is less than or equal to R, which is also less than x. However, if R were greater than 0, then x could not be the order of A mod m, because R would be a smaller positive integer for which a to the r would be congruent to 1 mod m. That would contradict the fact that x is the smallest such integer. So this is impossible. Thus, r must be 0 and n equals qx. That is, the order must divide n. In particular, if we remember from Euler's theorem, a to the phi m must be 1 mod n. I'm sorry. Man, this is getting me heavily confused. Switching my n's and m's all over the place. Sorry. Right, okay. Right, okay, this is fine. Right, so okay, I'm sorry. Switching up my m's and n's. A to the phi n is congruent to 1 modulo n. Thus, we know that from Euler's theorem. Right. Yeah, okay, yeah, I'm still confusing my n's and m's. I'm sorry. We know a to the phi m is congruent to 1 modulo m. That means the order, by our now proven theorem, the order of a modulo m must divide phi m. Before we concluded that it had to be less than or equal to phi m, now we know it must actually divide it. Alright, now that's out of the way, let's do an Amy problem. Find the least odd prime factor of 2019 to the 8 plus 1. I apologize, as said, but the superscripts are messed up in this PowerPoint. Alright, well, suppose P is an odd prime factor of 2019 to the 8 plus 1. That means 2019 to the 8 is congruent to 1 modulo P. Square both sides. 2019 to the 16 is congruent to 1 modulo P. So, the order of 2019 modulo P must divide 16. Note P in 2019 have to be prime because 2019 is 3 times 673, and for them not to be relatively prime, P would either have to be 3 or 673. In either case, that would end up with a 0 marginal p, which is what we know has to be 1. So they're relatively prime. So and the order has to exist. Alright, so the order has to divide 16, meaning it is equal to either 1, 2, 4, 8, or 16. I claim it cannot be 1, 2, 4, or 8. For example, if it were 1, then 2019 to the 1 would have to be 1 mod 16. Raising both sides to the 8th power would give 2019 to the 8 would have to be 1 mod 16. But that's not possible because up here we concluded that it had to be minus 1. So it can't be 1. Similarly, if the order were 2, we could raise both sides to the 4th power and obtain the same contradiction. If it were 4, we could square both sides and end up with the same contradiction. Finally, if it were 8, then we have a direct contradiction. Alright. So if it can't be 1, 2, 4, or 8, it's got to be 16. Alright, so the order is 16. But we know the order must divide phi of p, which is p minus 1. We figured this out previously. That means 16 divides p minus 1. The first two odd primes that are congruent to 1 modulo 16 are 17 and 97. There are actually an infinite amount of them by a theorem. So the first two are 17 and 97. We can test both of them manually, and after a lot of computation, it's not much fun, I know, but during an AME, this is what you gotta do. So you test both in 17 and 97. 17 ends up not working, but 97 does. So that's our answer. Right, so here's a JMO problem, which is good practice of what you've learned in this lecture. Prove that there exists infinitely many pairs of relatively prime positive integers a, b, which are greater than 1, for which a plus b divides a to the b plus b to the a. Don't forget to use Euler's theorem on this question. Try to, figure out some pairs that do work. And I'll leave this problem to you. So I hope you enjoyed this lecture. If you understood this lecture and understood the contents of our modular arithmetic handout, then I'd say you're fairly well prepared for all number theory that appears on the AMCs, the AIME, and even JMO, really. These are congruences, Euler's theorem, Chinese remainder theorem, orders. These are pretty much the most frequent topics that are used in math competitions. So yeah, you should be fairly set. There are more advanced topics, but you really don't see those advanced topics popping up until you reach, maybe the later USAMO level. So this is about it. All right, hope it was helpful, and see you next time.